We are in Chapter 5. In Chapter 5, we're going to look at some of the applications of the definite integrals. So coming out of Chapter 4, we actually define the integral initially as the area under the graph of a positive function. That's how we define the integral from a to b of f of x dx. And then later on, we managed to take on the idea of the Riemann sums, and the definite integral turned out to be the limit of the Riemann sum. And then for that segment, we really did not need to define the definite integral as an area under the curve anymore. It could be other things as well. So in Chapter 5 now, we're going to take a look at some of the applications now of the definite integral. These applications all define the attribute as the limit of Riemann sums. So the buzzword here is the limit of sums. Okay, so everything that you see in section 5.1 through 5.7 will be expressed as limit of sums. So in section 5.1 is what we're doing in this section. We're going to take a look at the area between two curves. Okay, so let's begin with this work. So again, the idea here is to do the following. In general, let's say I have a couple of functions here. Let's call these f of x and g of x. So let me do a general drawing here. Okay, my two functions are, suppose, let me use different colors. I'm going to use, this is my function f of x, and then I have another function, let's say g of x would be something like this. Notice that f of x lies above g of x. True? So that function is actually, the function above is higher, it has higher value, function value that is. Okay. Now if I mark the region between them, I'm just going to highlight that maybe with a different color. There you go. This region that is bounded between them, that highlighted region, this is all we want to do in this section. I'm interested in finding the area between these two curves. Okay, and we're going to look at the area stretching from A to B over that interval. The region is this region R. Okay, and that's all we want to do. So f of x here is the upper boundary of the region, and g of x is the lower boundary of the region. So in this setup, we're going to assume that f of x is greater than or equal to g of x. Okay, and that they're both positive, okay, over an interval from A to B. And it's really that simple. That's all we want to do. We want to find the area. Now, we've already found the area in this form. Remember, if we had a curve like this, and this would be from A to B x. Remember, we managed to find the area like that. Well, this is a special case of the more general region that's up above it. Okay, and let me show you, because here's G. Look at G is this x-axis, right? So in this case, G of x would be 0, right? So we never saw g of x as a function when we did it earlier as the area under the curve. Okay, so it makes sense that the work we are about to do is very consistent with the kind of work we've done earlier. So we can actually, it turns out we can actually define this region R in terms of, or express as a limit of Riemann sums. Okay, so let's actually begin with our, we have a theorem here. Okay, this theorem is actually a definition of area of a region between two curves, right? And it goes like this. Suppose we have f and g. Okay, we have two functions, and let's say these are both continuous, and as I have it above, f is greater than or equal to g. Okay, and this is for all x inside the closed interval running from A to B. then the area, which is what we're interested in, the area A of the region, is going to be, of the region, bounded, that is bounded by the graphs of f and g between x equals a and x equals b, is given by the following Riemann sum. The area, just as before, is going to be the definite integral from a to b of simply f of x minus g of x dx. And again, in the case where the region looks like this, g of x is 0, so we get the familiar f of x dx. You see that? We are used to seeing that one in previous chapter. And that's all this is. Okay, so what turns out is that if we have, let's say, this region now, and all we got to do, if we take a look at, let's say, some interval, a random interval, call this interval, let's say my usual notation, x sub k minus 1 and x sub k, right? That would be the kth subinterval. And here, remember, we have c sub k, or evaluation point, which could be right endpoint, left endpoint, midpoint, whatever, wherever that is. At that point, we construct a rectangle here, and then the area of this rectangle is what we're interested in, right? So this would be f, and this is g. Now the upper limit of the rectangle, because I'm trying to find the height of the rectangle, right? If we go height times width, then we have the area of that selected rectangle. So this one would be the coordinates of this point is c sub k and f at c sub k, which gives you the height of the rectangle at that point, and or not quite the height, but it's the upper boundary of the height. The lower boundary of the height is going to be again c sub k and given by g at c sub k, right? Now the actual height of the rectangle is this, right? This is the height of the rectangle, and that height is given by f minus g. Okay, so that's pretty easy. And the width of the rectangle, we always take it to be a regular partition. That means the width is going to be the usual delta x, which becomes differential of x dx. Okay, so from this, and then of course we're going to have a whole bunch of these rectangles, right, over the region from A, let's say, to B that's bounded. The region must be bounded, folks, so we can find this area. If we have unbounded region, of course, the area does not exist. Okay, so now we can actually express the area now actually as the limit of as the norm of the partition goes to 0 of sigma k1 to n of f c sub k minus g evaluate at c sub k. This gives you the height of the rectangle times delta x sub k, and this notation allows for any partition. Remember, p here is a partition, any breakdown of the number line of that interval from a to b actually, and the double lines means the norm, right? Norm, the magnitude of the longest segment in that partition. That's what that is. So when we talk about the norm, therefore we allow for delta x to be different. Again, although in practice we choose them to be equal to make it easy for ourselves. So this area, therefore, is going to be the limit of Riemann sums, ends up being the definite integral from a to b of f of x minus g of x and then dx. Okay, that's what it turns out to be. So Remember, the limit of sums go from A to B, and this piece, this gives you the length again. This is the length of a rectangle, right? And dx would be the width of that rectangle. So you're looking at length times width, and the integral means you do this over the entire domain interval, length of the interval from A to B. Now, in this integral, we are integrating clearly with respect to x, right? And because we have dx, so the region is labeled as an r subscript x for that reason. R subscript x, that means your rectangles are vertical rectangles. Keep that in mind. For an Rx, we have vertical rectangles, and that means we use dx for the width of each of those. Okay, and that region Rx lies between f of x and g of x. Okay, now it is possible to find the area of this region, that's highlighted in yellow. We can find it another way. We can use horizontal rectangles to do that also, right? And I'll show you an example where how that's going to be done. But let's actually talk about that one. If the equation is of turns out to be of the form x as f of y now. So we have usually y as f of x. This time x is f of y. And of course f is continuous, right? We always want continuity here. And instead of interval from A to B, we're going to make the interval run from C to D now along the y-axis though. Okay, not the x-axis, but the y-axis. Then we can and then reverse the role of x and y, and we can find that area this way. Okay, now this time, of course, when we do, we're gonna get, let's say, for the different region, I'm looking at the different region, not the one I had above. Let's call this one x equals g of y, and the one that opens to the left, call that one x equals f of y. Okay, so that's going to be this curve. Okay, and the red curve, of course, let me remove that one, that's going to be the red curve. Okay, so we have those. Now this time I said you can use horizontal rectangles, so let's say that's my typical rectangle now. Okay, and let's project these now onto the y-axis. We're not going to do anything with the x-axis, but our partition now is along the y-axis, right, this way. That's our partition. And let's say the point of intersection here is C, the point of intersection of the two curves, D. The region is bounded between C and D, right? And there's a closure of the region. This time, instead of x, this is going to be y sub k minus 1, and the upper value is y sub k. So we're looking at the kth right in here. This would be the kth rectangle. Okay, now for this one, here's my evaluation point, right? So my evaluation point again is C sub k, and that's how I construct my rectangle. Okay, that's C sub k. Now the coordinates of the point, therefore, the coordinates, because I need to again do height times width, length times width, right? Well, the width is delta y now, right? That's the width. That's going to be dy or delta y. They're the same in this case, although we're going to use dy. Okay, and that's going to be, there you go, delta y sub k. They're almost equal. Okay, for an infinitesimal rectangle, because these rectangles are very tiny, and just making them bigger so you can see better. So what are the coordinates of this point there? The coordinates is going to be x comma y. Well, x is given by the purple. X is f of y, right? So this is going to be f at c sub k. That's how I get my x's. And of course the y is, in this case, c sub k, right? And the lower portion of that rectangle is given by g at c sub k comma c sub k, right? And so my rectangle, just to show you that rectangle, better drawing of that this is what the rectangle looks like. This point we just said that's f at c sub k, that's the x value, and the y value is c sub k. And this other point we said is g at c sub k, and the y value is c sub k. Okay, so notice this would be the height of the rectangle, or one side. Okay, this is the one side of the rectangle. Now the other side of the rectangle, right, the other side is just the thickness is what dy is. And if you multiply the length times width, right, this is length, and of course the width is dy. So the area is going to be length times width. The length is going to be the right function, which is f c sub k minus g at c sub k. That's going to be the length times width. And that will give you, what you call it, that will give you the area of that rectangle. So the area of the region now bounded between c and d is therefore going to be the integral from c to d, right, of f at c sub k minus g at c sub k times dy, right? And that area, of course, can be stated as the limit of Riemann sums. But that is how you just make the adjustment here. Okay. Now let me do an example. And that's all there is really in this section as far as the instructions. Now we actually have to put this to use, working with various regions. The key to our success here is to draw these graphs very accurately and consider the area as the limit of Riemann sums, draw our representative rectangles, and then just evaluate the integral. So let's take a look at an example. In this one, let's say I want to just set up the integrals. Set up the integrals that can be used to find the area. Okay, that's what we want to do. That's the area between two curves. And let me try x equals 3y. And my other equation is x equals y squared minus 4. So notice here's x is a function of y, and x is here another function of y, g of y. So let's do this. When I graph this thing, here's x and y coordinates. Now x equals 3y, right? X equals 3y. If you solve for y, we get 1/3 x, right? We know what the graph of that is going to look like, 1/3 x, right? So it's going to be a line that runs through the origin. True. Slope is 1/3, so that's x equal 1/3 x. That helps me to graph it. Now x equals y squared minus 4. This one is going to be a parabola, right? But this is going to be a sideways parabola. Remember, x equals y squared. These parabolas open to the right, correct? Like that. Open to the right, and so this is x equal y squared. Now y squared minus 4 will cause this to go back 4 units, right? It shifts it to the left 4 units, and you redraw it. So when I do, it's gonna look something like so. Okay, so this is going to be x equals y squared minus 4. So we have the line, right? This is x equals 3y, and we have the parabola drawn, and this is negative 4. Okay, now the region that we are interested in, let me highlight the region. This is the region of our interest, right? The region must be a bounded region, and that's where the bounding is, right there. Other places, like over here, that's an open region, right? Up here, that's open region, and so pretty much that's it. Alrighty, now let's do this. There are two ways we can do this. We can use horizontal or vertical rectangles. So how do we know which one? Well, again, some choices are better than others. Okay, some are better than others. Therefore, what we're going to do is see which one makes it easier to integrate, right? So let's choose horizontal rectangles. Okay, now for horizontal rectangle, I'm going to draw a representative rectangle. There you go. It's going to look like this, right? And again, evaluation point doesn't matter, right, left, end point, whatever. What we want to do is we want to use that rectangle. We need to draw it so that we can determine the height and the width of the rectangle. Of course, the width is dy. For horizontal rectangles, the width is always dy. For vertical rectangles, it will be dx. Okay, so there you go. That's dy. So I need to determine the height. Remember, to find the height, we take the function value on the right minus the function value on the left. Okay, in this case, f of y lies to the right of g of y. So this is f of y, the function that's on the right side. The function on the left side is g of y. Okay, and you always take the right minus the left. Okay, so the area is going to be. Now these rectangles, by the way, they can be drawn here. They can be drawn here, here, anywhere as you move over the interval here. And what is our interval? The interval is going to run from C to D, and that's how we need to determine C and D, by finding the point of intersection of the two curves. Okay, we'll do that in a moment. But you see how these rectangles can start from the lower limit C and work their way up, and they stop at D. And of course, the height of the rectangle is going to vary as you go over that interval from C to D. As you move from C to D, the height is going to be different. Okay. Now, to find C and D, we need to set the two equations equal to each other. So I'm going to set the parabola equal to the line was 3y, correct? So I'm going to set those equal to each other. And we're going to end up solving a quadratic equation, right? Now, for this quadratic equation, we can actually factor this. Y minus 4 times y plus 1 equals 0. So y would be 4 and y would be negative 1, right? Those are the points of intersection of those two. So C, which is the negative value of y, that's where negative 1 is, and D is 4. The upper limit is 4. So the limits of integration will run from negative 1 to 4. Okay, now the function to the right is the line, which is 3y. The function on the left is the parabola, y squared minus 4, and then dy. And there you go. That's how you set it up. And if we wanted to, we could actually evaluate this, couldn't we? We can find the area this way. But we just want to set it up. And there you have it. Simple. Now, one thing we got to be careful here. over the interval from -1 to 4, throughout that entire interval from -1 to 4, the function on the right side, right, the line lies entirely to the right of the parabola. So if these functions behave so that they could intertwine and intersect at several points, and they can flip-flop which function is to the right or to the left, then we need to take those into consideration to find these areas correctly. But for this one, we're done. That's the area. Okay. And now, what if I want to use vertical rectangles? Okay, so for vertical rectangles, let's redraw this thing. Remember, we had this line, and we had the parabola, right? That looked like that. This was x equals y squared minus 4, and this was x equals 3y. And this time, we want to use vertical rectangles. Well, for vertical rectangles, that means we're going to switch to y as f of x, right? So this, I need to now write this as y equal 1/3 x. And y squared minus 4, we need to solve that. So y squared is equal to x plus 4. Take the square root of it, you get plus or minus root x plus 4. So this portion, the part that lies below the x-axis, because y is negative, that's going to be negative square root of x plus 4, right? And the part that sits above this part, the branch of the parabola that sits above 0, above the x-axis, that is actually going to be square root of x plus 4. So that's what that is. Okay, notice we have two parts. So what about the limits of integration? Well, when I draw my typical rectangle, my rectangle is going to look like this, right? At that point, that's my vertical rectangle. And these rectangles can vary over, again, the interval. Where is the interval? The interval starts at -4. So there you see my rectangles could have different heights. There you go. That's what it looks like at 0. The rectangles must touch the upper function, and they must touch the lower function. So those are my rectangles. Every one of those have a width dx, right? The points of intersection, we already found those, right? This one was y -1, and this one was 4. Okay. Now, let's see, when the limits of integration for x now run along the x-axis. So it's going to go, our limit's going to go from -4, and the rectangles stop right in here, right? They stop at that point. So what is the x value at that point? Remember the point of intersection there, the y is 4, right? This point, coordinates of this point, we know y is 4. So if you plug in for y 4 in here, then x would be 12, right? X is going to be 12. By substituting for y, you can plug in for y of 4 in the parabola, it doesn't matter. That gives you 16 minus 4, again 12. That's the point of intersection. So -4, 12, that's for, again, we're using vertical rectangles, right? With vertical rectangles, that means we have an Rx region. The region that's above here, by the way, in here, this region is, that region is going to be an Ry region. Remember, subscript y tells you that the variable is y, and it also tells you that you use dy. So associate the subscript with dy. Okay, and that way, and dy means horizontal rectangles. If you associate the x with dx, dx means vertical rectangles. You see that? That's how you can keep the notation straight. All right, let's set this thing up. Now, as we move from left to right, this is tricky, so you gotta really pay attention. Okay, as we move from left to right, in the beginning, you look as I draw these lines, this function, the function above is the square root of x plus 4. The one below is a negative square root of x plus 4. So there you go. That's what it looks like. The function above, the upper branch of the parabola minus the lower branch of the parabola. Until we get to this transition point, the point of intersection. What is the point of intersection here? Well, this is when y was negative 1. And again, if I look at y equal 1, x equal 3y, x equals 3y, the line, that's the line. Well, when y is negative 1, that's going to be negative 3. So the coordinates of this point are negative 3, negative 1. Okay? Now, this is the transition point. At this point, we no longer connect the upper branch of a parabola to the lower branch of the parabola. At that point, there's a transition. We go from the upper parabola, the upper branch of the parabola, to actually we switch to the line. See that? So it's touching the line, not the parabola. Okay, so you got to be careful here. So that's where the integral is going to change. So let's track this. The area is going to be the integral from negative 4 and it goes to negative 3. The upper branch, the upper function is root x plus 4 minus the lower branch is negative root x plus 4. Right? And then we have the x plus. So this integral picks up this region. You see that? It picks up that region. Now we're going to move on to the next segment. Now, the line, this line actually lies below the parabola all the way to the end of the interval right here. And that we decided is when this is 12. So over the rest of the interval from negative 3 now to 12, the parabola and the line, the function above is parabola. This goes from negative 3 to 12. It's going to be the positive branch of the parabola. That's x plus 4, right? It's going to be x plus 4 above minus x over 3, right? Minus the line, and that's dx. Notice how much more complicated this got. This will be exact same area as this one. So that's what I was saying. Well, how do we know which one to use? Well, whichever one is easier to integrate. I would use horizontal rectangles here, although this would work. Okay. Now, let me show you an illustration of what we have done here, just using let me use a program to show you this this concept of finding the area between two curves, so it helps you even understand it better. Okay, so there you have it. Here, these are two different functions, of course. Okay, and in this illustration, the blue curve is like y equal x squared, and the red curve is the cube root of x. I'm just looking at in the first quadrant here. Now, x at 0, look at the beginning of these rectangles. Okay, of course, the width of the rectangle, again, is infinitesimal value, means like 0.0001. That's what the width is. So you don't see actual rectangle. The rectangle almost turns into a line here. But anyway, and note as I move from the lower limit on the x-axis, it goes from 0 to 1. Okay, the x will go from 0 to 1 here. That's from the point right here at the origin all the way to this point of intersection, which is at 1, 1. The graph on the right side is the same as the one on the left. Okay, so here as I move, you can actually look at the graph on the right side here. Okay, so if I move to the right, look at how these, see the rectangles, their heights changes depending on how they are bounded between the upper lower boundaries. And there you go, stop there. So you can only have these rectangles from the beginning of the interval, in this case 0, right, all the way up to the right endpoint, which is right there. That's where it stops, at 1. Okay, and that's how it is. So this, and then when we sum those, right, that would give us the area under that curve. All right, let's take a look at another example here. Okay, so in this example, we want to actually now find the area between two curves. Okay, so let's say one equation is 8 cos x, and the other equation, y equal secant squared x. And we're going to look at the interval from negative pi over 3 to pi over 3. That's where the point of intersection of the two is going to be. Okay, now if we take a look at the graph of this, just to help you see what the graph will look like, there you go, this is what the graph is. And let me move this up there. The function above is actually the cosine x function. Okay, 8 cosine x function. And that's what this one is. This is going to be 8 cos x. And the one below it is portion of the secant squared x. Right? Remember, the secant function looks like this. So we're just looking at one of those upturns. And this one is secant squared x. Now, for this one, I'm just going to go with vertical rectangles. So the vertical rectangle, for example, a typical vertical rectangle could go from here down to here. And if you look over the entire domain, the point of intersection here of the two, by the way, that's where pi over 3 is, and negative pi over 3 are. Okay, and that's where those are, because that's where the bounded region is. And over this entire domain from negative pi over 3 to pi over 3, the green function, if you will, sits above the blue function. So that means cosine lies above secant squared. Therefore, this is easy, and we just have to do one integral. So the area is going to be the integral from negative pi over 3 to pi over 3 of 8 cosine x minus secant squared x and times dx. Okay, and that area, now the integral of 8 cosine x is going to be 8 sine x, true, and the integral of secant squared is tan x. So pretty basic. And the limits of integration, of course, run from negative pi over 3 to pi over 3. And we just have to do the fundamental theorem now, right? The upper limit minus the lower limit. Now, one thing we can do in these, by the way, we can take advantage of the going symmetry here. So, for example, if you look at right at x equals 0, okay, these two areas are symmetric, right? The area to the right of 0 and to the left of 0 on the x-axis, there's 0. Those two areas are the same, aren't they? So we can often take advantage of symmetry here. The reason I want to mention that is because when we do the fundamental theorem, in this case, I have to plug in a negative pi over 3 inside here, and I'm going to have to evaluate those trig functions. It's much easier to evaluate them at 0, a lot of things, because they either eliminate or give us an easy to work number. So I'm going to do that. How am I going to account for this? Therefore, I'm going to go twice. Okay, twice the And I could have done that from the get-go also. In fact, let me do that. I can rewrite this integral as 2 times the integral from 0 to pi over 3. Not negative pi over 3 to pi over 3, but 0 to pi over 3 of 8 cosine x minus secant squared x. That would be exactly the same, wouldn't it? Because of the symmetry. So the answer is therefore going to be 2 times 8 sine x minus tan x, right? And that's going to go from 0 to pi over 3. And this will give me 2 times. Now, the upper limit, again, sine of pi over 3, that's square root of 3 over 2. And tangent of pi over 3, these are 60 degrees, right? So this is your 60 degree, that's your 30 degree. Remember the reference triangle looks like that. So sine of 60 degrees is going to be opposite to hypotenuse, root 3 divided by 2. Tangent, opposite to adjacent, is going to be root 3. And both sine and tangent at 0. When you do the lower limit for the fundamental theorem, you get 0. See how much easier that was? So all said and done, this will be 8 root 3 negative 2 root 3, right? Distribute the 2 and combine like radicals. The final answer is 6 root 3. And there we have this one. Okay. And we are done with this example. Let's take a look at another one. Okay, so this one is exercise number 4 in your textbook. The question says, reads, find the area. Okay, now I'm going to use, again, vertical rectangles here. Okay, because they're a lot easier to do than horizontal for this particular one. So a typical rectangle is going to look like that. The width is dx. And remember, as we go from -1 to 0, the red curve lies above the blue curve. Once we go from 0 to 1, you switch from 0 to 1, notice the blue curve sits above the red curve, right, for these rectangles. And the rectangles have to touch the upper and the lower function. So there you go. For this one, we actually have 2 integrals, therefore. The first integral runs from -1 to 0, right? Those are the limits of integration of the red curve, which is x squared, minus the lower one is x to a third dx. And then we add the integral from 0 to 1 of the blue curve, which is x to a third, minus the parabola. You see how we have to adjust for which function is positive and which one is negative. Now, the integration part is actually pretty easy. The first one is 1/3 x cubed. The second one is going to be x to a third plus 1 is 4/3. So it's going to be 3/4 x to 4/3, right? Evaluated from -1 to 0. Plus, this would be 3/4 x to 4/3 minus 1/3 x cubed, evaluated from 0 to 1. Okay, let's plug them in. We're doing the fundamental theorem of calculus now. The upper limit is 0. In for x makes it 0, minus the lower limit. It's going to give me 1/3 of -1 to -1 cubed, right? Minus, I'm plugging in -1 here and here, minus 3/4 3/4 of x, which is -1 to 4/3. So that's the upper minus lower limit, plus again the upper limit in the second integral. The upper limit is 1, so it's going to be 3/4 1 to 4/3 -1/3 of 1 cubed. Lower limit 0 gives you 0. Let me just say minus 0 if you want to write it, but no need to write that. Okay. Now, negative 1 cubed is negative 1, so this is going to be negative of negative 1/3, right? 1/3 times negative 1, negative 1/3. Negative 1 to 4/3. Okay, this one. That's cube root of negative 1 to the 4th. That's going to be 1, right? Because I'm raising to even power. So that's just going to be minus 3/4. And inside the bracket here, you get 3/4 minus 1/3 plus 3/4 minus 1/3. Okay, we have that. Now, negative and negative, they combine those, right? We're going to combine them, and then negative makes the answer positive to that. The LCD is 12. So that's going to be 3 plus 9, right? Plus next fractions, LCD is 12. That's 9 minus multiply top bottom of 1/3 by 4, you get 4. Okay, and there's 12. So the answer is going to be 12 minus becomes plus 12 plus 5, right? 12 plus 5, that would be 17. 12. Let me just check my arithmetic, make sure everything looks good. Let me see who actually write in here in the beginning. Sorry, this first fraction, remember the LCD is 12, so you multiply top bottom by 4, so that's going to be 4, right? And then plus top bottom by 3. Yeah, that looks good. That looks better now, in fact. So that means those actually cross out to 0, so the answer is going to be 18/12. Okay, 18/12, and both divisible by 6, so we get 3/2. There, that looks good. Okay, and there is the area. Now, if you want to do horizontal, we could, right? We could do that, but this is going to be more work. For one thing, for horizontal rectangles, let me just draw this thing. Hold on. And let's see. Let me paste my graph there. So I'm just going to set this one up. Okay, we're going to set this up using horizontal rectangles. Okay, but we won't actually finish it because it will take longer to do this one. And sometimes, even though we set it up, but we may not even be able to actually integrate it because the integrand doesn't have a closed form, so we have to approximate, do numerical integration. But let's do this piece right here. Okay, now remember, I'm using horizontal rectangles. So when I use these horizontal rectangles, and they're going to go from the point of intersection, looks like from -1 to that point of intersection doesn't quite look like 1, right? So we'll verify the points of intersection of these two curves. Actually, let's see. It's going to be intersection of the line and the curves, right? So this point, when x is -1 this is on the cube root, so it's -1. Cube root of -1 is -1, so that's that point. This point on the parabola, when x is -1, you square, you get -1, 1. So we got those points. There's 0, and this is going to be 1, 1. Okay, so for this segment, the area is going to be the integral from lower limit on y is -1. Okay, we're looking at from -1 to 0 here. The blue function is x to 1/3. Now, we also, in here, if I cube both sides, I get y cubed equals x. Remember, for horizontal rectangles, we need to have a function of y actually, not x. So the function to the right is y cubed minus the function on the left now, right? What is the function on the left? It's going to be what? The y value is going to be, let's see, the x value, right? This is x equals -1, the vertical line. So it's going to be -1 minus -1. That's the x value. And of course, that's dy, right? Limits of integration go from -1 to 0. Plus, that just picks up the lower portion of that region. Okay. And for this portion of it, now we need to add that area to it. Plus, that's going to be the area. It's going to go from 0 to 1. From 0 to 1 here, right? That's where it's going to go. And now we have the red curve on the right side. If y equals x squared, that means x equals 2 plus or minus root y. The left branch is going to be where x is negative, so that's negative root y. The right branch is going to be positive x, means positive root y, because I'm in the first quadrant x is positive, second quadrant x is negative, so negative root y. Okay, and so the red function is negative root y minus -1 dy plus, so we pretty much accounted for this region. Two integrals for that, and now for this one. The red lies entirely to the right of the blue curve from 0 to 1, right? So we go horizontal rectangles, and see as you move from lower to upper limit, the red is always to the right. So it's going to be plus the integral runs from 0 to 1, right? 0 to 1 of the function on the right side is root y minus the function to the left, which is y cubed. Look at that, how much more complicated this is. And we can actually evaluate this integral. Okay, we can actually evaluate it, and maybe we'll do that just to make sure. The answer is going to be 3/2, but remember, the one we were already done with this, much easier. This is much harder way of doing it. Okay, let's actually evaluate the integral. The area is the integral from -1 to 0 of y cubed minus 1 is y cubed. I'm just writing it in a neat form now, and then we integrate it. Plus 0 to 1 of 1 minus root y dy, rearrange those terms, plus integral from 0 to 1 of that one is fine, root y minus y cubed, the way it is, dy. Okay, now let's integrate them. The integral of y cubed plus 1, 1/4 y to the 4th plus y from -1 to 0, plus the integral of 1 dy is y minus square root of y, that's y to a half. Half plus 1 is 3/2, so it's going to be 2/3 y to 3/2 from -1 to 0, plus the integral of, again, square root of y is going to be 2/3 y to 3/2 minus 1/4 y to the 4th and 0 to 1. Okay, the 0 in all of these, every one of these, upper limits, if anywhere you plug in a 0, you get 0. So for the first integral, upper limit 0, I'm just going to do the lower limit, right? So it's a 0 minus the lower limit. The lower limit, -1 for y, makes it 1/4, right? Minus 1. There. Plus the middle one, this one now. The upper limit for 0 gives it 0 minus the lower limit the lower limit, make it 2/3. And again, y to 3/2, that's square root of y, right? Cubed, y to 3/2 with a y cubed. Let's see. Okay, sorry. This actually, there's a sorry about that. This is going to go from 0 to 1, right? Right up here. I don't know what happened. So all the limits of proper, yeah, so that should be 0 to 1. Okay, now plug in, got to plug in the upper limit 1, correct? When I put 1, I'm going to get 1 minus 2/3. The lower limit 0 gives you 0, minus 0, plus the one next to it, upper limit 2/3 times 1 is 2/3 minus 1/4. Lower limit 0 gives you 0. Equals, and 1/4 minus 1 is 3/4 positive, and the negative in front makes this negative 3/4. And 1 minus 2/3 is going to be plus 1/3. And this one, 2/3, I'm just going to write plus 2/3 minus 1/4, right? So I need to combine these fractions. Okay, 2/3 and 1/3 makes 1, right? Negative 1/4 and 3/4 makes negative 1, so that will be 0. Okay, I see what happens. I see what happened. Nothing wrong with the way we did it. Now, of course, the answer 0 doesn't make sense, right? Look at this. The area doesn't look like 0. Now, here's what happened here. The answer is 3/2. Now, we need to make an adjustment. Again, nothing we've done here is incorrect. Everything looks good. But the very beginning, when we set up this area right in here, okay, remember that's the definite integral is for this lower portion of that area, right? Now, when we did this, this integral is going to be negative, right? Because the area lies below the x-axis. So this is going to be a negative area. But because we want to force it to become positive, we know area cannot be negative. If we want to interpret this as an area, we have to force it to be positive, right? So in the very beginning, we need to make an adjustment. We're going to make that a negative, right? Again, the reason justification for the negative on the first integral, definite integral, is because the definite integral naturally for this will be negative because the function, the area lies below the x-axis. So that's the adjustment we have to make going forward in all of these. So I'm going to go a equals negative of that. And now that I've explained it, hopefully that makes sense. Okay, and that's equal to, this is going to be negative, and now that'll be positive. Okay, let's reevaluate this one. Now, for this one, 1/3 and 2/3, again, that's 1, right? And then we have plus 3/4 minus 1/4 is 1/2. So it's going to be 1.5, and that's going to be 3/2. Okay, so again, everything we did was right. We just have to be really careful. There's so many subtle details in this work that make things go wrong. But anyway, this is how you actually do this. And we are done with this exercise. Let's take a look at another one. All right. So what I have done now is I have brought some of these exercises that we're going to look at together. So the ones I have circled are the ones we're going to work together here. Okay. Let's begin with our first exercise, number 12. And for all of these, if we can graph the region, I really recommend, because without a visual of the region, it's very difficult, if not impossible sometimes, to recognize the limits of integration and see how these functions interact together. Sometimes they cross over at more than one place, so we really need to graph these accurately in order to be able to set it up correctly. So let's begin with exercise number 12. In exercise number 12, the question reads, sketch the region bounded by the graphs of the given equations and find the area of that region. So in number 12, the region is given by y, which equals x squared minus 4x. So that's going to be a parabola. And y equals negative x plus 4. So that's going to be a line. Okay. Now let's actually graph this thing and see what it looks like. As far as the parabola goes, if you factor this, you get x minus 4, and the x-intercepts, that's when y is 0, so x is 0 and 4 are the intercepts. These are your x-intercepts. Okay, and the y-intercept is, anytime x is 0, then the y-intercept is 0, 0 naturally. So this is going to be 0, 0, and the other place 4, 0. Now, as we graph this thing, on future ones I'll try to maybe use Desmos or GeoGebra to graph those, so you get a better graph. But for this one, right now, here's a 0 and there's 4, let's say. Okay, and then the vertex is going to be halfway between those two, 0, 4. The parabola is going to open upwards because the coefficient on x squared is positive. Vertex is going to be at the x component of the vertex is going to be negative b over 2a. That's negative of negative 4 divided by 2, or 2. Yep. And when x is 2, you get 4 minus 8, and right, I'm trying to find the y component, so 2 squared minus 4 times 2. That's 4 minus 8, or negative 4. Okay, so the vertex is going to be at 2, negative 4, right in here. And we can draw the parabola. That's that branch of it. The other branch of it, of course, is going to look like so. And then we need to graph the line, correct? The line is easy. Slope is negative 1, y-intercept is at 4, so this is going to be 4. Let's say here, that's 4. The x-intercept is when x is 4, so it actually crosses right in here. Perfect. So my line, therefore, is going to look something like this. There. So this is going to be the graph of those two functions. This one, 4 minus x, and the parabola, of course, is x squared minus 4x. Again, in this course, at this point, we should be able to graph these without graphing calculators. All right. Now, let's see. The bounded region is this region. True? There's no other region that's bounded. We have open region here, open here, open here, open here. So we're not interested in the open regions. They're not bounded, so their area would be infinite. Now for this one, we can actually set up our integrals, and it will be easiest to go with vertical rectangles in this one. Okay, of width dx. So that's what we're going to do. We're going to set up a vertical rectangles for this. Now, that means a typical rectangle is going to have width dx, right? The height of the rectangle is given as a distance from the upper function to the lower function, right? Therefore, when we set up this integral, and these rectangles, by the way, then they can start right here, and then you can see as you move across. So they can begin with the point of intersection of the curves and go all the way up to 4. Now to find the point of intersection of the parabola and the line, we set y for line equals to y for the parabola. In other words, we go 4 minus x equals x squared minus 4x. Move x to the other side, it becomes positive, so that's negative 3x minus 4 equals 0. Okay, or right. And then sure, that looks right. And then we can factor this one. We can go x minus 4 times x plus 1, right, equals 0. And x would be 4 and negative 1. And here's at 4 where they cross. The other place they cross is at negative 1. All right. And we're good to go. Therefore, the area is going to be the integral. And over the entire interval from negative 1 to 4 on the x-axis, the line lies above the parabola. So we don't need to make any adjustments. I'm just going to go equation of the line minus the equation of the parabola. X squared minus 4x dx. And there you go. Pretty simple integral to evaluate. So this would be negative 1 to 4. Now just working the specifics of this. Put the number first. Like terms, negative x and plus 4x, that's positive 3x minus x squared dx, right? And we can easily evaluate this integral. The integral of 4 is going to be 4 dx is going to be 4x. 3x would be 3x squared over 2. And negative x squared would be 1/3 x cubed, evaluated from negative 1 to 4. Okay, and now I can do my fundamental theorem, upper minus lower limit. So the upper limit, 4 times 4 plus 3/2 times 4 squared, negative 1/3 times 4 cubed, minus the lower limit, 4 times negative 1 plus 3/2 times negative 1 squared, negative 1/3 times negative 1 cubed. Okay. And this would be 16 plus, in the middle I have 16 divided to 8 times 3, that's 24, right? 24, and minus 64/3. That's the first one. Minus the bracket is going to be negative 4 plus 3/2 minus 1/3. Okay. And in here, when we work all of these out, let's see, this is going to be the 40, right? 40, so the be 120 minus 64/3, combining in parentheses, the first parentheses, minus the second parentheses, combine these into one, the LCD is 6, negative 24 plus 9 minus 2, right? So it's going to be negative 26 plus 9, negative 26 and 9, that's negative 17, right? Negative 17/6. All right, and then the LCD, so let me just put one more step here. This will be 56/3 negative of, let's see, did I do that one right? Let's see, I have negative 1/3 plus that. Let me just make sure I got this right. The LCD was 6, that's negative 24. This would be 9, right? Minus 2. So it's 26 minus 9. Yeah. 17/6. Okay, and the negative in front makes it positive. 17/6. Now the LCD is 6. That would be 112 plus 17, right? Oh, I actually, hold on. This is going to be positive, right? There's a positive 1/3 there. So that means in parentheses, that's going to be negative 24 plus 9 plus 2. Now that's 11, 24, 13. Yeah, this will be positive 13/6. Alrighty, looks better. I knew something wasn't quite right here. So this was the adjustment I made. That should be positive. Okay, so all said and done, still the fraction remains 125/6. That would be the answer to this one. So the area under the curve is going to be 125/6. And again, we could have done this with horizontal rectangles, but they would have been much harder to work with horizontal rectangles. And the reason is because, for example, my horizontal rectangle goes like this. Now you got to find the equation in terms of x of the left branch and then the right branch. So there's definitely more work involved in there. And your limits of integration, once you change it, once you go from here to 0, remember this was -4, go from -4 to 0, and then you switch the function to the linear function on the right side as you go from 0 to the upper limit, right? Which is 5. So anyway, much easier to do it with vertical rectangles. Now, let's take a look at, we did 12, let's take a look at number 20. In number 20, we have 2 root x minus x equal, and the other one is y equal negative root x. So I've already graphed these, the ones I've circled in Desmos, so I'm just going to bring them over to help us see these. The graph of these, of course, will be more involved, right? Or, for example, something like this one even. These graphs are more involved, not as easy as the other one. Something like this one, for example, right? So we definitely use this graphing utility to help us out. Otherwise, it will take too long. So let me bring these graphs over. We're doing number 20. Okay. Let me do this. Okay, so here's number 20 and the graph that goes with it. Okay, so the function negative root x, that one is easy. We can do that without the software even. Remember, square root of x looks something like this. Negative root x reflects it. So that's the reflected version. Okay, that's going to be the one below. That's negative root x. Let me put it here. Negative root x is this one. And then the one above, which is a slightly more challenging to do, you could go through our graphing procedures to do that. But this would be the graph of, the red is actually the graph of 2 root x minus x. Okay. Now, for this one, again, if we look at the point of intersection we need to find here, and we find the point of intersection by setting the two equations equal to each other. Because at that point, the points of intersection, looks like there's going to be two of them. They have exact same coordinates. So if I add root x to both sides, I get 3 root x. Bring x to the other side. Square both sides, I get 9x equal x squared. And then x squared minus 9x equals 0 by factoring. I can find the points of intersection to be 0 and 9. And that's what we see here on the graph. There's 9 and 0, the origin. Now, and we only need one integral, right? So if I use a vertical rectangle, the rectangle is gonna go like this, and evaluation point doesn't matter as long as it touches the curve right there. So the rectangle will have width dx. So that means I need everything in terms of x, a function of x. So for this one, the area is going to be the limits of integration. These rectangles can start from the beginning and work all the way to the end, which is at 9. They stop at 9. I cannot have rectangles beyond 9. Okay, so therefore I can write this as the integral from the limits of integration 0 to 9 of, this would be 2 root x minus x, right, the function above, minus, let me use parentheses here, minus the function below, which is negative root x, and then dx. Again, this would be like height times width for each rectangle. And that means we have the limits of integration ranging from 0 to 9 of, if I simplify this now, again, the double negative on root x makes positive. 2 root x and root x makes 3 root x, which I can write as 3x to a half minus x dx. Okay, and then integral of 3x to a half would be 3 times a half plus 1 is 3 halves. Invert, you get 2/3, and x to 3 halves here. Okay, and minus integral of x is just going to be 1/2 x squared. And then evaluate it from 0 to 9. And this will give us the 3's cross out. So upper limit, you plug in, we get 2 times. Now, 9 to 3 halves. True, negative 1/2 times 9 squared. The lower limit gives you 0. When you plug in 0 in for x, we get 0. So the area is equal to 9 to 3 halves. That would be square root of 9 cubed. So that's 27. 27 times 2 is 54. Negative 81 halves. And that's going to be 108 minus 81 halves, combined fractions. And we get 27 halves for the answer in this one. Again, simple and really easy if you do dx. If you try to go horizontal rectangles on this one, good luck. Because right in here, when you write x as a function of y, that's going to be impossible for you to do because the way this looks. So it's going to be a lot easier to do it this way than to choose horizontal rectangles. But if you could, then we expect the same answer. Maybe on the next one that I use both methods. I'm sure we have exercises coming that will ask us to do it both ways. That means horizontal and vertical rectangles. So we did number 20. Now let's take a look at number 24. X root 4 minus x squared. That would be 2 1/2, right? Okay, so for number 24 again, let me write it. This is, we have y is equal to x times 4 minus x squared. Square root of that's to a half. Okay. And what else do we have in number 24? And y0, right? This one. And y0. So the region that's bounded between y0 and the one that we just wrote. And this one, y0. Now y equals 0. Remember, that is the x-axis, right? So here's what this graph's going to look like. There's a graph that of this function, And of course, y equals 0 is the x-axis. Okay, now we can do a couple of things. First of all, notice this graph is symmetric, right? Now, because we want to find the area, if I just do the integral from -2 to 2 of x root 4 minus x squared dx, I bet you that would be 0, right? But we're told to treat this as the area under the curve, so that answer is not acceptable for us because we want to find the area. Now, to do that, we have two choices. We can either, although the definite integral from -2 to 0 will be negative, force that into a positive area, or go twice the integral from 0 to 2. In other words, double up on this one. So however we do it, it's going to work out fine. Now the choice, vertical versus horizontal rectangles. If you go horizontal rectangle again, the challenge is to find a function of y for actually, see how these rectangles vary up to here to the max. So one thing, we need to find the extrema of this function, then find an equation for the right side, an equation for the left part of the curve. So this is going to be very complicated, right? We really don't want to spend time doing that. Even if we could, it's just going to be very tedious and cumbersome. So let's do what I recommended maybe, in that we're going to double up the area. And this function indeed is an odd function, because if you look at negative x, I'm changing f of x with f of negative x. 4 minus negative x squared to a half. This becomes negative x, 4 minus x squared to a half, and that's negative f of x. So we just showed f of negative x is equal to negative f of x. So the function is indeed odd. And that's another reason this will be 0, right? Using properties of definite integrals and the fact that the function is odd. Now, the area, then I'm going to go twice, double up on 0 to 2 of x root 4 minus x squared dx. That'll be the easiest way to do it, right? So a rectangle is going to look like this, right? And that's a typical rectangle with dx. The height of the rectangle is given by the red curve minus blue, which is 0, right? The x-axis. And this one we can actually work it nicely using a u substitution, couldn't we? If I let 4 minus x squared be u, then negative 2x dx is du. Now we already have, see, 2x dx. We can build that in there. Therefore, I can just write it this way. I can say 2x dx is negative of du. True? And just swap out 2x dx, those for a negative du. That's going to be the integral of u to a half du. And then negative, of course. And remember, anytime you change the limit, the variable of integration, I change it from x to u. We need to change the limits of integration. So when x was 0, u will be 4, and when x is 2, u would be 4 minus 2 squared, 0. So the limits of integration used to be x0, now is 4. X was 2 upper limit, now it's u0. And we can do another thing. Notice how 4 is bigger than 0. So those limits of integration, usually we go from lower to higher. So I'm going to change the limits of integration to go from 0 to 4. Remember the offset. When we do that, that makes it negative here, right? The integral will be negative of the original integral, negative of negative u to a half du. All said and done, this is 0 to 4 of u to 1/2 du, which is so easy to evaluate now. Half plus 1 is 3/2, so this is going to be 2/3 u to 3/2. Evaluate it from 0 to 4. Plug in a 4, so I get 2/3, 4 to 3/2, right? Minus 0 to 3/2, which is of course 0. Now 4 to 3/2, that's square root of 4 cubed. 2 cubed is 8, so that's simply 16/3. And there we have the area found relatively easily. Using vertical rectangle is definitely the option for this one. Okay, let's take a look at the next one. This next one we're doing is number 30 and 34. Okay, I will write these down so I don't have to keep scrolling. Number 30 and 34. All right, in number 30, this is number 30. So for 30, we have a square root, or actually it was 1 minus x, right? Yes, number 30, it is root x plus root y equals 1, and then x plus y equals 1. Okay, that's number 30. And let me bring the graph up for this one. Okay, so here we have the graph. Now let's actually set up this integral. I'm going to go with vertical rectangles. Again, these vertical rectangles can go like this. The width would be dx. The height is given by the red curve minus the purple curve. The red is x. The equation for the red curve, of course the line, is y equal 1 minus x. And for the purple one, if you solve for y, well, square root of y would be 1 minus root x. Square both sides, right? So for this one, and for this one, y would be 1 minus root x squared, right? And let's see something real quick. All right, it looks good. So it's going to be 1 minus root x quantity squared. Cool. Now we can set it up. The area is, limits of integration go from 0 to 1, right? From here to here. That's when the rectangles can move from left to right. So it's going to be 0 to 1. And the integrand is going to be, the upper curve is 1 minus x minus the lower curve, which is 1 minus root x quantity squared, right? And then the x. There, that would be the area. Now we need to just tidy up a little bit here. So that's going to be 1 minus x. And if I square the binomial, I get -1. -2 times 1 times root x with a negative on the outside makes positive. That's going to be positive 2 root x. And then, of course, root x squared is positive. Negative in front makes it negative x. Root x squared is just x. And then dx. And let's work this one out. Combine like terms. So 1 and -1 adds to 0. So this becomes just 2 root x and a -2x. The x's become like terms. And we can now integrate this one. Factor the -2, by the way, if you like. And the integral of root x, remember that's x to a half. True, so that becomes 2/3 x to 3/2, right? And the one next to it is just x, so the integral of that is -1/2 x squared, evaluated from 0 to 1. Now the lower limit in for x will give you 0. So I'm just going to plug in the upper limit here. Plug in a 1, and 1 to any power is 1. So this actually reduces to an easy expression, -2, and then 2/3 minus 1/2. That's all that becomes. True. That's -2. The LCD is 6, so that's 4 minus 3, and 2 6s 1/3, so the answer is going to be, of course, 1/3 on this one, right? And let's see, make sure I did this right. Oh, I factored in -2 out. Actually, no, factored a 2 out, not -2, because I could factor a -2, but because I kept that as a negative, then let's just factor a 2 out, not -2. Now it looks right. Okay, and there you have it, number 30. Let's take a look at the next one. This next one is number 34. Okay, so here's a graph of number 34. Let me write it down. In number 34, we have actually trig functions in number 34. So the red one is the graph of cosine, or of sine actually. This is, the red is sine x, and the one next to it in purple is cosine of 2x. Okay, the equation is y equal cosine 2x, y equal sine x, and then region that's bounded between x0 and x to 3 pi over 2. Now remember, x equals 0, that would be the y-axis, right? And x equals 3 pi over 2, that would be a vertical line at 3 pi over 2. True. So let's do this. This is going to be right here. That's that. Now this is at pi over 2 right in here. The low point is at pi over 2. Actually, that's at pi over 2 pi. This is 3 pi over 2 right in here. Okay. And let's see. Actually, you know what? Right, sorry. That's not pi over 2. Okay. Looking at the sign, this is going to be, actually, that's where it's pi. And this would be pi over 2. Okay, and right in here I have the vertical line drawn at 3 pi over 2. Okay, that looks better now. So the region, let me maybe highlight this region that we want to find the area of. So this is the region. It's going to be that. And then we have this portion of our region, right? We have this part. We need to find the area of that. And then once we have done this one, we need to find this area, right? So notice now, for some intervals, there's actually a change over from red to blue, if you will. And we need to always make sure in our integration we use the higher function, right? We want to use the upper function minus lower function. So in exercise number 34, therefore, Now, where do these going to cross, these two curves? I need to find these points of intersections, right? In here, here, and of course, this looks to be 3 pi over 2. Okay. So let's set the equation equal to each other. Cosine 2x equals sine x. Okay, and then we need to solve this one to find their point of intersections. Now, cosine of the double angle, cosine 2x, I can write this as 1 minus 2 sine squared x. Bring the sine over, equals 0. So I have negative 2 sine squared x, negative sine x, plus 1 equals 0. Multiply everything by negative just to make it a positive. The coefficient on x squared will be positive this way. Minus 1. Now we get a quadratic equation here, quadratic in sine. I can factor this hopefully, sine x. Two numbers, the product is negative 1. Let's see, so my choices are not that many choices here, right? And because it's 2, I put 2 in front of this one. So let me go with plus 1 and negative 1 like that. And when you do the OI in FOIL, we get sine x, so I'm good with this. Sine x equals 1/2 in one, and sine x equals negative 1 in the other. Now remember, our interval, we are between 0 and 3 pi over 2, right? So sine x equals negative 1, that means x should be negative 3, or I'm sorry, sine is negative, so that means x is 3 pi over 2. And that is this point right here. That is 3 pi over 2. Now, the other one, sine x equals 1/2. Well, sine of 30-degree angle is 1/2. So that means x must be pi over 6 and 5 pi over 6, right? In the interval from 0 to 3 pi over 2. Means 0 to 270 degrees. Sine of 30 and 150 degrees are both positive 1/2. So that's what we found here. This point, the first one, is pi over 6, and the second point is going to be 5 pi over 6. And we are good to go now. So we can set up our integral that will find the area of the bounded region between them. So first integral, going to go from 0 to pi over 6, right? Limit of integration is that, and this would be upper function is cosine. Remember, the blue is cosine. So here this is cosine 2x, and this is cosine 2x. This is cosine. The red is sine. Okay, so this would be sine x, and this is sine x. Okay, so upper minus lower function, that's cosine 2x negative sine x dx, plus the integral from pi over 6 to 5 pi over 6, right? This time the higher function, the upper function minus the lower function. That's going to be cosine of 2x dx. And finally, for the last piece, plus the last piece, cosine sits above sine. That's from 5 pi over 6 to 3 pi over 2. It's cosine, again, 2x minus sine x dx. All right. And then we have to just do the integration now. The integral of cosine 2x, you can make a u substitution here and let u be 2x. So du would be 2 dx. Okay. And therefore 1/2 du would be dx. So as indefinite integral, the integral of just cosine 2x dx reduces to the integral of 1/2 cosine u du. And the integral of cosine is sine right? Plus the constant of integration. All right, and of course the integral of sine is going to be negative cosine. Now I can finish this off. The integral of cosine 2x, therefore that's going to be 1/2 sine 2x plus cosine x, right? Because negative sine, integral of sine is negative cosine, double negative makes positive. This is from 0 to pi over 6. Okay, and then plus it's going to be next one, negative cosine x, the integral of sine, minus, we just did cosine, right? 1/2 sine 2x. We just did cosine 2x right up here. Evaluated from pi over 6 to 5 pi over 6. And then plus the last portion, which is 1/2 sine 2x, 1/2 of sine 2x plus cosine x, and that's evaluated from 5 pi over 6 to 3 pi over 2. There. Now the upper minus the lower limits, so let's plug them in. 1/2 2x, that's 2 times pi over 6 is pi over 3. Doing this one, sine of 60 degrees, pi over 3, that's going to be root 3 divided by 2, plus cosine of pi over 6 is root 3 over 2 also, right? Now be careful, because of this 0, don't just go 0 when I plug in for x you get 0. You're not going to do that with trig functions. Only with algebraic function, when you put 0 for x, the value becomes 0. So I need to actually evaluate this. Sine of 0 is 0, plus cosine of 0 is 1. You see that? So make sure for trig functions, even if it's 0, you plug them in. So that's 1. That's the first one. Plus the integral. 5 pi over 6. And that's 150 degrees, right? Right in here. Reference angle is 30 degrees. Negative cosine. Cosine in the second quadrant is negative. So cosine of 5 pi over 6 is going to be, what, root 3 over 2 negative, and negative in front. That's just root 3 over 2. Minus sine of 2 times 5 pi over 6. That's going to be 5 pi over 3, right? So this is going to be, let's see, 1, 2, 3, 4, right? 60, 120, 180, that's 3, 4, and there is 5 pi over 6. Okay, and let's see, sine of 5 pi over 6 is going to be, or actually, sorry, I'm plugging in 5 pi over 6 times 2, that's 5 pi over 3, correct? 5 pi over 3. So that's pi over 3, 2, 3, 4, and 5 pi over 3. Wow, that's going to be, So 6 pi over 3 would be 2 pi, right? 106, 5 pi, that's 60, 120, 180, there you go. 1, 2, 3, 4, 5 pi over 6. 5 pi over 3. There. Now, sine of 5 pi over 3, the reference angle is going to be pi over 3. So that's going to be root 1/2 root 3 over 2. Okay. And what do we do next? Next, we need to plug in the lower limit. The lower limit, this is the upper, minus cosine of pi over 6. That's going to be negative cosine of that is going to be negative root 3 over 2, minus 1/2 sine of 2 times pi over 6 is pi over 3, sine of 60 degrees. Pi of, that's root 3 over 2. Okay, And that's this one. Plus, oh my. And the upper limit is, this will be easier, 3 pi over 2. Sine of 2 times 3 pi over 2, that's sine 3 pi. So that first part is 0. And then cosine of 3 pi over 2 is 0. Plus 0 is 0 minus 1/2 times sine of 5 pi over 3. Right, we just did that one. Sine of 5 pi over 3. That was, let's see, 60 degrees. Hold on, 5 over 60 degrees. The reference angle is actually 30 degrees, so this should have been a half. It should be a 1/2. Okay, hold on, let me make sure I got this right. Okay, I think I got this correct now. So let's see, everything should make sense and everything should be straightforward. Again, you plug in the upper limit and lower limits. You can do a quick check to see that I've got all of these measures done correctly. So let me now simplify this one. I'm working on the first set here. So when I simplify that one, the LCD is 4. So that's going to be root 3 plus 2 root 3, right? Minus 1. The term next to it, negative 1. This one. And moving to the middle part, this part. Now, in this part, I can combine, this is going to be plus root 3 divided by 2 plus root 3 divided by 4. Plus distribute the sign, root 3 divided by 2 plus root 3 divided by 4. And there you go, that one is done. Plus the last set of brackets, this one. You go positive root 3 over 4, right? Positive root 3 over 4. And negative times that makes it also positive. Closing parentheses and brackets. Okay, now I distributed it. So it's going to be plus root 3 over 2. Okay, and that looks good. Now I can combine all of these together. Keep negative 1 aside. Everything has a square root of 3 in the fractions, right? So let me do this. Here's LCD of 4. 2 root 3 and root 3, that's 3 root 3. Correct? Over 4. And then I have plus this one becomes 2 rad 3 plus next to it root 3. So that's done. And then this one plus 2 root 3 plus next to it is another root 3 plus another root 3 plus 2 root 3, right? Minus 1. Now if I count how many like radicals there are, 3 and 2, 5, 6, 8, 9, 10, 12. So I have 12 radicals, and 12 by 4 is 3, so that's 3 root 3 minus 1. Boy. The arithmetic of that one is what took so long. Okay, so anyway, that's going to be the area under between these two curves in number 34. Okay, and I think, let me just check to make sure that this is all we want to do. So I'm going to pause and return. Alrighty, let's take a look at this last exercise in this section. Exercise number 44 reads, find the area of the region bounded by the given curves. In part A, using integration with respect to x, and B, using integration with respect to y. Well, with respect to x, that means you have to use vertical rectangles. X and dx go together. With respect to y, you have to use dy. That means horizontal rectangles. So for this one, let's actually graph this function. It shouldn't be difficult to graph it, right? First, the square root of x, that's the square root of x. And then we have 1/2 x. That's going to be the half x, right? 1/2 x. That's going to be a line through the origin. Okay, and this was the square root of x. And the other equation, y equal 1, so that's going to be a horizontal line at 1. And y equal 2. Now that I got to be careful with, because let's see, when y is 2, square root of 2, and y equals 2/2 times 2, that's 1. So that's actually the point of intersection of these curves, right? Okay, I want to know where the radical function and the line cross out. Okay, that means 2 root x equals x squared both sides. We get 4x equals x squared plus or minus 4x equals 0. So factor the x, you get x minus 4 equals 0. Okay, so at 0 and 4, that's where the radical and the line cross. Okay, that's good information to have. And square root of 4 is 2, so that is the other part of that line. Yeah, y equals 2 goes right through there. So I'm just going to move my 1 a little higher here. There you go. That's more realistic now. Excellent. So we have y equals 2, y equal 1, the two horizontal lines. Then we have the slant, 1/2 x. We have the radical. Therefore, the region of intersection of all of these, or the bounded region, I should say, is this region. Correct? That is the bounded region. Now, the question first is with respect to x and then with respect to y. So let's do that. With respect to x in part A, that means we have to use vertical rectangles, right? Now, if I use vertical rectangles for this one, let me do a blow up of that region. Looks something like this. Vertical rectangles, the upper portion, the upper function, I should say, is given by square root of x. The lower one is given by the line, right? The lower portion is this is the line, 1/2 x. Okay, so in part A, therefore, the area is going to be, and the limits of integration, by the way, got to be careful actually. This is going to be split into two parts because look at the lower function. Okay, again, let me do a bigger picture here for you. It looks like this, right? Of that shaded region in red. So, and I've really, it's not drawn to scale, but just to make you see. Now, look at the lower function. Here I have a line up to this point, right? The point of intersection of the slant line and y equal 1. So this is going to be at 2, right? Because y is 1. So this is going to be 2. You plug in 1/2 x equals y needs to be 1, right? And from this we get x is equal to 2. So that's where the slant crosses y equals 1 at x equals 2. And I can write the area now. Let me actually label these here. This is y equal 1, right? So the limits of integration go from 1 to 2 here, right? From 1 to 2. And that will pick up the first part of that area, this region. And then the other part goes from 2 to 4, right? That's this other portion from 2 to 4 of the square root and then the slant line, right? So that's, notice the lower function switches to the line 1/2 x. This one is just 1, right? Okay. And we take y equal 1 to be a g of x here. That's our g of x. All right, we're good to go. Now I can write the integral in part A. That's going to go from 1 to 2 of the square root function, right? Square root minus the lower function is 1 dx. And the second part is going to go from 2 to 4. 2 to 4 of, again, the upper function is the radical, the lower function is the line. Half x dx. Okay, and then we can actually integrate this now. The area is equal to square root of x to a half. The integral of that would be 2/3 x to 3/2 minus the integral of 1 dx is just x. From 1 to 2 plus again the second integral, 2/3 x to 3/2 minus x squared over 2 makes this x squared divided by 4, evaluated from 2 to 4. And now the fundamental theorem, we're going to plug in the upper minus lower limits. And I'm going to need probably a long line for that one. So a is going to equal to the upper limit 2/3. That would be 2/3 times 2 to 3/2 minus 2 negative. Plug in a 1, we get 2/3 times 1 to 3/2 minus 1. Done with the first integral. Second integral, 2/3, 4 to 3/2, negative 4 squared is 16/4. And then minus the lower limit is going to be 2/3, 2 to 3/2, negative 2 squared, 4 over 4 is 1. Okay, now let's see. The first term and next to the last term are opposites, they add to 0. Correct? Now let me pick up the pieces. Negative 2 here. I'm moving from left to right inside, moving left to right inside the brackets. That's going to be negative 2, and then this piece would be 1 to any power is 1, so that's just negative 2/3 plus 1. Distribute this negative as you go. And then this one, 4 to 3/2, that's square root of 4 cubed. That makes it 8. 8 times 2, that's going to be 16/3, right? Oh, hold on. I said it, I didn't do it. Negative 1 and 1 makes 1. Okay. Now, so that's going to be 16/3 plus 16/3. And negative 16/4, that's negative 4. And finally, negative of negative 1 is 1 plus 1. Okay, so the constants, negative 2, 1, 1, negative 4. Well, there you go, those add to 0. And that's just negative 4, right? So we have negative 4 plus 16 minus 2/3, that would be 14/3, right? Now the LCD is 3, that makes it negative 12 plus 14, or 2/3. And there you go. That's using, again, what we did is you used vertical rectangles, correct? Vertical rectangles over the first portion, the vertical rectangle like that, that's dx. And from 2 to 4, our vertical rectangle looks like this, right? Of width dx. So the upper function is root x in both cases, but the lower function, notice, changes from constant to linear. So that's part A. Now in part B, the second part, we want to use horizontal rectangles in this one now. So let me redraw this with horizontal rectangles. Okay. Okay, so let me redraw this thing. Here we have, remember we had the portion of the square root, and then we have this piece by the constant function, and then we had the slant line, right? This was y equals 2, right? So that piece is y equal 2. That's the upper limit. The lower limit starts at y equals 1, right? And here's x. Okay, now using horizontal rectangles. Okay, these horizontal rectangles are going to go like this, right? There's one of them. The width is going to be dy. There's another one. Here's another one. There is another one. So that's the start of it. This would be the end of it up top. The numbers were 1, 2, 4 along the x-axis. Now, those don't matter because we're looking at everything projected onto the y-axis. Now, for horizontal rectangles, what we do need to do is we need to change our equations in terms of y now. Okay, before it was in terms of x. So for example, this was y equal root x. If you square both sides, we get x is equal to y squared. Remember, x must be a function of y now. So the function on the left is y squared. Let me write this one. This is y squared, right? The function on the left. And the function to the right, which is the line actually, right? This green line, whose equation was 1/2 x. That means x equal 2y, right? Okay, again, we have a function of y this way. So this is 2y. And once we have that, then it's easy. Limits of integration go from 1 to 2 of the right function. That's 2y minus the left function, y squared, dy. There you go. And this is going to be the area. Notice up here in part A, it wasn't bad either, but we had to split it into 2 integrals. We had to deal with the fractions, and that's what we did. So this might be a little bit easier. The integral of 2y is going to be y squared over 2, so that's just y squared. Negative 1/3 y cubed. Evaluate it simply from 1 to 2, so it doesn't involve any radicals or nothing. That's good. Upper limit makes this 4 minus 1/3 y cubed would be 8. Minus lower limit is 1 minus 1/3. So 4 minus 1, that's 3. And then negative 8/3 plus 1/3. Plus 1/3 minus 8/3 would be negative 7/3. The LCD is 3. 9 minus 7/3, 2/3. Notice how much faster, how much easier this was. So it really does make a difference sometimes using horizontal versus vertical rectangles. But what's important is that no matter how we do it, we should get the same answer, right? So just got to be mindful of that. And I think that's about it here. We did what we wanted to do, so we are done with section 5.1, area between curves.